I'm the electrical instructor, 104, here at Electrical Technology. Today, we're going to be talking about the periodic table of elements, how it is, how it works, and more importantly, at the end, we're going to be talking about the flow of electrons, which is electricity. So let's start by looking at the first element that we have here. What do we have?
Hydrogen.
Hydrogen. What do we know about hydrogen? Water what?
Well, with oxygen, it makes water.
Ah, there we go. Now you make a compound.
Yeah.
Okay, so an element is as small as we can get. You just named a compound, not to be confused with an element. So element is something that cannot be further subdivided. So we'll start, I'm going to try to do parts of the table here. So the first one we have is hydrogen. What do we know about hydrogen? Characteristics.
It's a gas.
It is a gas, yes, it's the lightest of all the gases, yes. What else do we know?
It's number 1 on the periodic table.
It is number 1, yep, number 1. Speaking from an atomic standpoint, inside hydrogen we're going to have 1 proton, 1 neutron in the nucleus, and on the outside we're going to have 1 electron. It goes in this orbit. And this is 1e, 1 electron. It would like to have 2 because of the empty orbit, the empty spot for an electron. There is enough space to put 1 there. I'll just mark it like that. Hydrogen really wants to have 2 electrons, but it only has 1. Since it only has 1, we've got a spare slot for an electron to go there. So where is that on the other side of your chart? What do we have that's?
This one.
Helium. Yep. He, helium. What do we know about helium? When you were a little kid, you went to the county fair and you had a balloon filled with helium, and you let it go and it went up in the sky. You said, "Daddy, Daddy." No. Where'd my balloon go? So I'm going to put an electron, and now we have 2 p's and 2 n's and 2 electrons in the outer orbit. What do you know about helium besides anything else? It's non-flammable. You can't do anything with it. It's got enough electrons in its outer orbit. It's very stable, very, very stable. You can't do anything. It won't burn, won't. It's just there as a gas. Okay, so much for the first line. Then we're going to jump on down a line. And the first thing we have under here is what goes in this box.
Now lithium.
What is it?
Now lithium.
Lithium. So I'm going to start another orbit up here. Around like this. This orbit can handle up to 8. But it's only got 1. So lithium has 1 electron in the outer orbit. It could have up to 8. Yep. 2, 3, 4, 5, 6. Yep. Could have as many as 8, but it's only got 1. So 3p and 3n. That's lithium. What do we know about lithium? Everybody should get this one. Lithium?
Good for batteries?
Batteries, yes. Exactly. Lithium is very popular for batteries. Why is it so popular? Because it has this 1 electron in the outer orbit, and it can be moved easily to something else. So we only use the word lithium, but actually there's other elements involved in this, and we're going to get to that in just a minute.
Boron.
Boron, yep. Interesting material. We don't do much with it. I'm not going to dwell on boron. What's the next one after boron?
Carbon.
Aha, carbon. Now if I was to draw a diagram of carbon, which I'll attempt to do here, lithium is 1. What's alongside of lithium? Oh, beryllium. What's this? Beryllium, Be. Okay. And then we pick up boron, carbon. What comes after carbon? Nitrogen. After that comes what? Oxygen. And after that, what goes? Fluorine. And the last one is neon. So if I was going to draw this, and it's getting harder and harder to draw it, so if you'll let me, I'll have this. I'll have up to 8. 1, 2, 3, 4, 5, 6, 7, 8 in the outer orbit. As we said, lithium is pretty good about having 1 electron. Beryllium is a lightweight metal used in aeronautical. NASA is a big user of that. Boron, I'm going to skip boron because there really isn't much application for that. But carbon, tell me a little bit about carbon, what you know about carbon.
Carbon dioxide.
Carbon dioxide, but that's a compound.
Yes.
Yeah, so that can't work as an element. Okay. Keep going. Scratch our head a little bit on.
Carbon fiber.
Yes, exactly. Carbon has 4 atoms in its outermost orbit. And carbon is a wonderful mixture because the orbit is half filled up. The other half is vacant. The half that is vacant can receive electrons or share electrons with others. Nitrogen, what do we know about nitrogen?
Laughing gas?
No, that was helium. Okay, what do you know about carbon? We use it every day. Carbon comes in so many forms. Wood, there's carbon in wood. What we use carbon for is for hydrocarbons. Hydrocarbons like gasoline, that's a hydrocarbon. Many elements, or pardon me, many compounds have as a basic building block carbon. And carbon is pretty good. What about this one? Nitrogen? You're breathing it in even as we speak. We're in a room full of nitrogen. Nitrogen is a gas, okay? And the air we breathe is composed of 80% nitrogen and 20% oxygen. You need the oxygen, your body needs the oxygen. It doesn't need the nitrogen, but the nitrogen goes along with it. So when you're huffing and puffing, or breathing naturally, you're going to 80% of this, 20% oxygen. So far, so good? Okay. What's the next one?
Fluorine.
Fluorine. We use, one of the uses at the governmental level here in Manatee County, we have fluoride in our water. As an additive, it helps prevent tooth decay. That's what the dentists say. Fluorine is another element that we don't use a lot here. And what's the very last one? Very last. Neon. What do we know about neon?
Colors.
Neon colors, especially at the local bar, if you will. The local bar has a big sign out front that says open, and it's lit up with neon. These are all inert. These over here tend to conduct pretty good.
What would be the difference between a neon light and then like a LED light?
What's the difference between a neon light and an LED light? It couldn't be further. You couldn't differentiate them anymore. It's really very good. Neon is an element. The light-emitting diodes, or LEDs, the light-emitting diodes, that's entirely a different chemistry. And it falls into, if I can jump down a line, let's start back on the left side, number 11. What do we know about sodium? Salt. You mix the two together, sodium and chloride, you get table salt, which is a compound. So far, so good? So what is emerging here? We'll jump down to sodium. Sodium is very flammable in the air. It'll self-ignite. I'm going to jump through some of these because they really don't apply to us. Magnesium, then jump over to the far side. Oh, here's one, number 13. What is number 13?
Aluminum.
Aluminum. What do we know about aluminum?
Conductive.
It is that, yes. Aluminum is conductive. What else about aluminum?
It's a metal.
It is a metal, yep. And they use it in lightweight applications like airplanes. Airplanes are built, although increasingly, airplanes are being built out of fiber composites, carbon fiber. Okay, what else have you? Back, number 14 is silicon. What do we know? Silicon. What do we know about silicon? Silicon Valley. You ever hear of Silicon Valley?
Yeah.
What do you think happens in Silicon Valley? They're big users of silicon.
Makes sense.
It's also there's some compounds that are silicates, and a silicate, a good example of a silicate is sand. Anna Marie Island sand. Let's just jump to the next one. Phosphorus. Phosphorus, the military likes phosphorus because when they shoot a gun, the gun bullet lights up, and it's basically phosphorus burning on the tip of that bullet. Sulfur, you know the compound sulfur, H2S, H2S, hydrogen and sulfur emits a gas, and the gas really stinks. Smells like rotten eggs. When we mix the hydrogen, two hydrogens and sulfur, we get that bad smell. But let's jump over to chlorine. You see a lot of chlorine around town. Swimming pools use it just voraciously. I mean, and the last one is argon. Argon is another gas, which is inert. So what we have here is we have conductors on this side, and we have inert on this side. What do you think we have in the middle? If we have conductors on the left side, and we have inert gases on the right side, what do we have in the middle? We have semiconductors. Makes sense? Conductors over here, semiconductors, those four are used in making computer chips of all types. These four elements are mixed together, and they form the basis of transistors, diodes, SCR, silicon controlled rectifiers, and chips, all kinds of chips. I'm going to jump briefly down to the next line. We're going to work along here. By now we've got 19. We filled up the first orbit with 2, the second orbit with 8, the third orbit with 8, and now we're down to 16 next orbit. So as we go along here, we're getting further and further from the nucleus, further and further, and it's easy to knock an electron out of that and displace it with something else. So we'll run quickly through this. Potassium, calcium, scandium. I don't even know what that's used for. I'll be truthful. Titanium. What do we know about titanium? It's a lightweight metal, and it's used by the people at NASA that builds the rocket ships. They have a lot of titanium in there. Next one over is vanadium. It's another element that we don't have much use for. Chromium. Now you wonder where the bikies get their chrome from? This is where they get the chrome. Manganese. 26 is Fe, iron. And then we have two here, cobalt and nickel. Now those deserve special emphasis because those two elements go with lithium. So you have lithium on one side, and the other two elements, nickel and copper and, cobalt and nickel, on the other side, and the electrons pass back and forth. So when you discharge it, all the electrons are moving toward cobalt and nickel. And then when you charge it back up again, it moves the opposite way. There's a problem with lithium, however, and it's a rather serious one. Where does lithium come from? %80 of the world's lithium comes from the Democratic Republic of the Congo. If you watched the news last night, I think the president got shot. Politically, it's a very unstable country. They've got rebel gangs shooting at each other, shooting at the government. So it's very, very hard. 80%. Now, where's the other 20%? We've got some of it here. Other countries in Africa have some of these rare earth metals, but it's a slog to get them because of the instability of the government. Let's jump right along. Nickel, we said iron, and by the way, if we took iron, number 26 and 24, chromium, that's how we make stainless steel. The chrome is mixed in with the iron. Moving right along, number 29. There's our friend right there, copper. So copper has electrons in the outer orbit that are easily displaced. That's nice to have. But copper does one, it's very conductive. The other thing is it's very cheap. The 14-2 wire that you're going to be using out there, which is copper, costs about 37 cents a foot, give or take a little bit. So iron is relatively cheap, and more importantly, it's malleable. In other words, you can bend it several times, just like a paper clip, and it'll stay together. So hold your thoughts on that one. Let's jump up to number 13, back up to the top, is aluminum. What do we know about aluminum? Well, aluminum is also a good conductor. Howsoever, we like copper the best. So you can sample the weight, relative weights of those two things. Yeah, aluminum is light, isn't it? Huh? Yeah, it really is. Really is light. Yeah, so aluminum would be much better if we could alloy it correctly. We did use a lot of aluminum back in the mid-'80s.
Which one's better?
Well, this will pass electrons.
Yeah.
Right now, all the electrons are just loafing in here.
Yeah.
They're not moving at all. This tends to be very malleable, as I said. This would be better, except you do experience some corrosion with aluminum. Not nearly as bad with copper. So you can set up aluminum oxides of aluminum, and that. The other thing that happens is when you squeeze down on this to terminate a lug, you tend to squeeze this quite hard, and it has a tendency to flow. In other words, you've compressed it so tight that it flows out away from the junction, becomes a loose junction. Loose, not so good, because it'll catch fire. So much for that. Now let me digress just a little bit. Okay, let's take these in our hand. This is straight out of the box. Circuit breaker. You'll be seeing a lot of those. Look at the verbiage on this. Look at the verbiage on the side of the panel. Bakelite, that's what's on the side. What do you see printed over there?
This?
No? On the side, yeah. What does all that say?
This stuff.
Interrupting rating, 10,000 amps,
Okay, keep going. You haven't hit the spot yet.
50, 60 hertz.
No, that's okay. That's not the spot. They're correct that it's there, but that's not where I'm angling for. Did you see anything about CU?
Oh yeah, the
Oh yeah, huh?
was that AL?
What is AL?
Aluminum, right?
Aluminum, yes.
Yeah.
So this circuit breaker can be used on either one. It says so right on the side of the. Now there are some circuit breakers that say you can only use copper. You can't use aluminum. So read the nameplate data is what I'm suggesting.
I was like, is this the like degrees under the 60 and 75?
60 and 75 degrees, that's the temperature rating
Yeah.
for the cable that you're going to be using when you go to fabricate the panel.
So like for aluminum, it would be 60, and copper, or not copper?
No,
Or is that just in general?
that's just in general. So you see a copper, you see this,
Yeah.
and you also see aluminum. Again, most circuit breakers, when you get one in the palm of your hand, hold it up to the light, and it'll tell you all about the circuit breaker, what the specifications are. You'll be doing this a lot. By the way, this little 15 here, that's amperage. So this is a 15 amp circuit breaker. We'll get into that more. Got it? Make sense? Okay. So these are circuit breakers right out the box. See the little flag?
Yeah.
What do you think that means?
It's off.
It's what?
Off.
Well, it is off, yes. What it means is that the circuit breaker has targeted out. In other words, it's opened up due to an electrical current fault. So the circuit breaker tripped, which it's supposed to do because it was overloaded. You'll see that a lot more as we go along.
So that's a good thing, or?
Well, yes, it's a good thing because it saved the circuit, because the circuit was heading for disaster if it didn't get there. But it's not good because you wired it up and you had a short circuit. Never good to have a short circuit. And this will tell you that something's wrong. And then you as an electrician have to go out and figure out what's wrong with this setup. And we will trip certain circuit breakers quite frequently here. So getting back to the board, we've moved a lot of different electrons around. The ones we're really interested in is copper and aluminum. You'll see some other metals out there. Sometimes the students ask a question, is there anything better than copper? Yes, there is, mercifully. Let's take a look. Take a look at number 47. Number 47.
Silver.
It's what?
Silver.
Silver. Yeah, great. Silver's a great conductor. Yesterday, silver went for $24 an ounce. Per ounce. That wouldn't even give you one strand of this. Ah, silver, $24 an ounce. Let's look on down another one. How about 79? Gold. Yesterday, gold closed at $2,500 an ounce. So gold is off the bus. It would be nice if you could afford it. It would be great. But at $2,500 an ounce, you're not going to build much of a cable system for that. Okay, let's look on to the left. 46. Palladium. Palladium's another heavy metal. Palladium is a little expensive, maybe $600 an ounce. Boy, this is getting a risky business. Let's look on down over 78. Ever hear of platinum?
Yeah.
Yeah. Platinum is about $1,100 an ounce. It would be wonderful if you could make it cables, but you can't afford it.
Yeah.
Can't afford it. Let's see down here, another one. Palladium 46. That's a good one, palladium. But again, it's expensive, very expensive. So what this is all leading toward is copper's our best bet, as you can see. We have a lot of copper here in the States, out in Utah, Wyoming. And again, copper's malleable, has good conductivity, and it's easy to make the electrons flow down the wire. So far, so good?
Yep.
Makes sense? would you like to make some electricity?
Sounds good.
Sounds good? Okay, I just happen to have a device that does just that. So let me introduce you to how we make electricity. Well, we've been through this copper thing, and we agreed that copper was a good deal. So what I have here is a copper, hold it this way. What I have here is a copper, roll of copper here. And this red and the blue, that's my magnetic field. Yeah, it bites. Huh? And so I have this magnetic field, and you can't see it, but the lines are there that go back and forth. And then what you do, now that you've got the copper and the magnetism, the third thing you need is a relative motion between the two. In other words, something has to move. Well, in this case, it's going to be the rotor. And so this little gizmo, which is supposed to demonstrate, let me do it that way. Let's do DC first. That's all there is to it. Electricity is not complicated. We make it more complicated than it should be. Get the gist? We have a magnetic field. We have a relative motion between the two. In other words, this is spinning inside the magnetic field. And we've greatly reduced it's like a 9-to-1 reduction. For every one of this, you get 9 of these. This goes around once, something like that. And you get like 10 turns, so it's geared down. Now, obviously, I can't stand here all day and crank this thing. We got to come up with something better. And that's what you pay the power company to do, is come up with something better than this. Although the principle, which is what I'm interested in, the principle remains the same. All generators, like your automobile generator, it's got a magnetic field. Might not use this, might use electric magnetic field. And it has a copper conductor. Switch over to AC. That was the DC, direct current. This is the alternating current. Not quite as bright as... With alternating current, they go out and they come back. They go out, come back. So the electrons start at the power plant, and it's copper. They've got something just like this. And it goes out to your home and back. So it's alternating, back and forth, back and forth. It does that 60 times in 1 second. So those electrons are moving very rapidly. So that's the difference between AC and DC. AC alternates back and forth. The electron goes from the power plant to your light bulb, from the light bulb back to your power plant, back and forth, back and forth. But it doesn't wear out the electrons. The electrons are, this is a cakewalk for electrons. They can go much, much faster if need be. But we, in the United States, we use 60 times. Now think about this. In 1 second, there's 60 times going back and forth. In a tenth of a second would be 6 cycles. Okay? So 6 cycles is as fast as you can blink your eye. It really is moving on. Now, pretend this is electric cable. This is what we're doing. This is this, and this, same thing. Now, there is no electrician. This is what you cannot do.
Well, that's like on something, like that's on.
Yeah, you visualize this as the circuit to your house, okay?
Yeah.
So you cannot go and, in the brief time that it took to touch that, a tenth of a second, those electrons have gone from the power plant back to you 6 times.
Yeah.
These electrons are moving, right? Back and forth. So we call that 60 cycles. And that's how we make electricity. Easy, right?
So if you were to put that on that and touch it, Did you get shocked?
Probably not. It's not high enough voltage to make any difference.
So you wouldn't feel it if you touched it?
Probably not, because this is very low voltage, very, very low. In other words, the electrons are not being pushed very hard. But what you pay for in your electric bill is somebody to turn the shaft. How can we turn the shaft? Well, we could use a steam turbine. We could use a steam engine. We could use solar panels. We could use windmills. Windmills are pretty good out in the Midwest. We see a lot of windmills. Now we'll remove the magnetic field and see what we get. AC. There's no magnetic field. The lines from here to here are missing. The magnetic field, lines of flux, they're called lines of flux. They're missing. So I have to put it there with, now we've got a magnetic field. Haven't changed anything in the copper, but that's all there is. Electricity 101. So let's see where we've come today. Let's wrap this thing up. So we've looked at the periodic chart, and we've looked at the different elements that are in our purview. I don't go much below that 16 line. So we've looked at the different atomic structures and what those electrons in the outer orbit can do. And then we've paired them up. Like if I had 2 hydrogens and 1 oxygen, I would have water. Water's a compound, though. We've taken a look at the conductors on the left side of the chart, and we've looked at the inert elements on the right side of the chart. And then we've looked at the semiconductors in the middle. Fortunately, silicon is easy to get, by the way. So we've looked at that, and we've looked at the different cable components. You could have copper or aluminum, and it'll tell you on the side of the circuit breaker. Look, when you get a circuit breaker out, always read the nameplate data. There's a raft of information. Just picking up the breaker and see what it says, what the specifications are. Bar work, most of it will be 15 amps, maybe 20 amps. That's what we use in residential for the lights that are in the kitchen, things like that. Then we transition from this and this over to the real thing. Again, you need a magnetic field. You got that. You need a conductor, which these are the conductors, this copper inside, and you need a relative motion between the two. So you have to do make sense? See right here. And then we've talked about a little bit about electricity. You'll be doing much more of this copper and aluminum, mostly copper. In today's world, it's about 99.9% copper. There is still some aluminum cables that we do use out there.
Do you use aluminum for? Is it just they used to use it in the past or something? They just kept it, or?
Where you'll see it is the conductor from that the power company installs from your transformer that sits up on the pole, and they run a service to your meter. That wire is likely to be aluminum wire. We use them for most everything. You're going to see up to 480 volts. That's as high as we go, 480 volts. That'll all predominantly be a copper wire for obvious reasons. It's malleable, and it's cheap, and it's good. Sorry I can't sell you on the gold or the silver or the platinum, but any comments? Okay, so we've taken elements from the left side of the page and gone down 5 different orbits. Each one of these are arranged in an orbit. We've looked at that. Looked at a generator. Looked at cable. Your next lesson is going to be on Ohm's law. That starts in level 1, I think chapter 5. And I'll have a series of presentations to do on Ohm's law and the power law. It's not hard. if you can add, subtract, multiply, and divide, you can do Ohm's law. So don't let the math torque you out, so to speak. And we'll help you over the humps with the math. It's just not that hard, but it does require some explanation. Questions, comments? I would thank our video photographer here, Monica. Thank you very much for our lesson here. And with that happy note, we'll conclude Electricity Elements 101. Class adjourned.